So thanks for the opportunity to be in the room without the mask. It feels good. So I'm going to talk a bit about waves in granular media. Maybe there is the pointers somewhere. This one? Yeah? Thank you. So just bit of context. So Gonzalo Tancredi is a colleague from the astronomy department in the Institute of Física in Montevideo, and this work is also done with Camila Sedofeito, who is somewhere around here, and also Bruno Dominiguez. So a bit of context where we study impact in granular media. Well, the objective is to understand what is going on in asteroids. So asteroids are granular media. Maybe you didn't know that. So this is a picture of a Itokawa asteroid. The scale is like 1 kilometer or maybe 2. And so you clearly see that it's many different sizes of rocks, and they just are together by autogravity. Okay? And one of the observations that also somehow prove that it's a granular media, that if you plot the diameter of this object and the spin rate, there is something going on right here, and it's named cohesionless spin barrier. So it means that if it would be something solid, you can rotate faster and have some bodies around here. Okay, so and there is also many other observations that some dust around some asteroids and other tails, and that's why in astronomy they are interested to know a little bit about what is going on in this granular media. So the question are how asteroids react to impact. It's very fast impact. So other piece of rocks in space can shock like at tenths of kilometers per second. So how the seismic wave travel in this body, and is that responsible for this material loss that we can observe, and some other feature like criteria deficiency. So before I have the question like Anne, why would we study that? You can just don't look up, and but you can also try to understand some. For example, there is this DART experiment, which means double asteroid redirection. The T redirection test. So the idea is that you have two asteroids, a big one like 700 meters and a smaller one 100, 200 meters, and they will send a spacecraft and impact the small object, and with the frequency, I mean the time of the orbit that you can sense from Earth, measure what is the moment you transmit to the asteroid in order to deflect his trajectory, for example. So that's the kind of reason why impact in granular media can be interesting to understand. So the thing is that there is a big difference between what we can do here. So there is some data from Mars, but from asteroids, I think we don't have anything yet. So we are on Earth, so there is a big difference with the gravity. And here, the minimum gravity is the atmospheric one, and in these bodies is like microgravity. So well, we study this. The idea that here that we change the pressure, because the microgravity will mean that the pressure inside this body will change a lot. So we change the pressure, but clearly we are not in the real case of asteroids. So how to extrapolate this result? Well, the idea that this kind of experiment will be used for as input and in models like discrete element models when you can take out the gravity. Okay. Okay. So one of the other question is if you study what is different between impacted and non-impacted waves, like with a shake, as I will show. Because, for instance, NASA they could send in a geostationary orbit to do an experiment, so it's more easy to just make a little push on the granular media than to do a real impact. Okay. And the other questions are more physical. What is the stress-strain relationship and how the wave behaves in this media? Sorry. Okay, so this is what our asteroid looks like. A bit different. So it's like a cube of 50 centimeter side, and we have like a wall press in order to apply a confining pressure with a hydraulic jack around here. We can measure the pressure here. We can just see the displacement with the camera. We have a chronogram to measure the projectile speed, and inside the granular media, so one of the granular media can be a mess, but you have one little advantage: you can put sensor inside the media. Okay, so we just put an array of accelerometers, and we fill up the box, and we have the measurement of the wave inside the media. And that's somehow how it looks. So we have the accelerometers, and we also have internal pressure sensors inside the box, and we'll resell some projectile on the top where there is it's open around here. Okay, so we can all the box is going up, and this part around here is fixed. So this is the kind of material we study. We have 3 different ones: so like spherical glass beads, and some kind of sand, and gravel, which is the same material with different size. And so it's around half a millimeter for the glass bead, around 1 millimeter for the sand, and more around 2-3 millimeter for the gravel. This is the kind of observation we have when we plot. So we press the box, so we just increase the force in our hydraulic jack, and this is the displacement we observe. So it's going up and going down, so it's kind of very hysteresis, and it's never going back at the original position. So you have a lot of rearrangement, non-reversible, also some reversible. That's how to say. Sometimes it can be leaking. I mean, the box. Sometimes it's vertical force. So if you go, the force is here in this direction. Yeah. And this is also vertical displacement. Yeah. Yeah. Before doing that, we just press a few times to have a bit more stability, because there is some variation. And if you do some average, I mean, with a few cycles, you can see something like that. So in the confining pressure in kilopascal, and this is now we have in strain. And you see in the compression, you have something like that look like elastic, and when you go back, it's strongly hysterical. Strangely, it's much more repeatable when you go down than when you goes up, and like there is kind of a change of the effective elasticity. So the slope, I mean the inverse of this slope,
and you can see in all the material that this is in glass bead. On gravel and sand, you have kind of an increase on the how compacted or how hard is the media. The order of magnitude here, it's around 10 megapascal, and it's very, very different in 2 order of magnitude lower than what you expect if you use classical effective medium theory, which is around 149 megapascal for the sand. So clearly we are probing something else, that what is going on between just the contact between grains is much less stiff. And there is the evidence of compactation, something here, and this strong hysteresis when we goes back. Okay. When we look at the internal stresses we measure inside the box versus the confining pressure, there is a lot of spatial variation. These little dots, it's a 2 centimeter diameter pressure sensor, and they are just one close to the other, like 2 centimeter one to the other. And you have huge differences between, like, let's say, this one and this one, and that's very characteristics of the granular media, where you have a strong chain forces. So there is a lot of scales of, I mean, compared to the grain size, I mean, the grain size of millimeter scale, so it's very different scale, but still you see a huge difference. If you do some average, you have something here, still red is for going up and black for going down. So it's somehow, it looks like proportional in the, when you're going up. This one sigma x is in the direction of the force, and the other one is in the other direction. So somehow you can compute a redirection factor between both of these red curves, and you have something that is equal to 0.2, and it's kind of if you look at the literature, it's kind of a clue that it's a frictionless media. So just taking into account the normal force contact between the grain, you have this value. So, and then when we go down, it's another one more time. There is strong hysteresis, and there is, like, here we are above, here we are down, and in the case of on the side, it's like nothing is going on, and then it go down. So it's kind of complex also when we relax the media. The reason why we're interested in what is going on in the pressure into this media is that into the asteroid, we don't know exactly what is the pressure repartition. So we need to know a little bit what is in our case, and in this easy case, well, easy. Simple case, it's not easy. So inside the asteroid, it should be more complex. Okay, so now let's move on the wave part. So we have experiment with projectile and also with just a shaker on the grain. And how we send projectile? Well, we can not use fire guns, so because the university is not allowed. But we use like this rifle. It's like a the little 5.5 millimeter diameter, around 250 meter per second. So we are really far from the kilometer per second scale of what is a real impact. So that's something that and we try to change the projectile and the speed to have some difference. But clearly you will see the result, but our range in kinetic energy is go from 2 to 29 joules, and it's not enough to see a real difference from the the impact velocity of the impactor. So that's how we do the experiment. With a shaker or with some this one is the crossbow, and that's the kind of signal that that we have. So we have 3D accelerometer, so we can look at the x component in this direction. So it's the main component, and this is the depth inside the box. So we clearly see a wave propagating, and on the other direction, in the y direction, we also see the other component, and so we clearly see we can measure some effective wave speed. That's another example. Here you can also somehow see that there is a reflection from the back around here, and here you can see that if you use like a classic correlation method of this signal, we can measure the wave speed. 5 minutes? Okay, so just have a look at the frequency as a function of the pressure. It's very stable for the measurement with the shaker, and there is a bit of an increase with the impactors. It's not so much, but there is something here going on, and this is the result of the wave speed as a function of the confining pressure in the with the shaker with the shaker. So in this, we still have the same code, color code. Red is increasing the pressure, and gray, black is going down. So you see that for the wave speed propagation, it's not really is theoretical. I mean, in this, around this a little bit, but then a high pressure, you cannot see any difference. What else can we say? Yeah, it's very high the dependency you have. So you go from 200 to almost 800 meter per second, and it was kind of hard to understand compared to what you can find in the literature about the dependency, the confining pressure with the wave speed in granular media. So I just performed some simulation, elastic simulation, to be sure that what we are measuring is really what is going on, because we have reflection from the back and from everywhere. So I just want to make sure that we are measuring really the wave speed. So really quickly, if we just simulate elastic 3D simulation, and with just air, not really air, but with a strong impedance contrast, you have something like that. So it's the K-wave toolbox, and here we have the source. So sorry, but it's just flipped. It should be the source on top, but for the numerics, it doesn't change anything. So we see the wave propagating here, and that's what we are following and in the media. And if we plot this along this line, so that's the one of thing that we can see here. This is a propagation along 1 meter for wavelengths that the smaller wavelength that I have. It's when we have in the low pressure range, and I just plot 1 meter. So the box is this side, just to see one thing, that the P and S wave, they are here. So this is the P1 and this is the S1. So where we are measuring, everything is mixed. Okay, so we measure something that is a mix of the P and the S wave. But if you measure this is here in red, the wave speed with the correlation, you measure something that is close to the P velocity. Is very close. And if you close the box now, so this is here when you have some reflection, well, you have something a bit different. So that's the dotted curve. Close to the end of the box it's totally wrong. But where we we have our accelerometers in this around this place. It's close to the computational wave speed, and oh, sorry. And if you look at the apparent wave speed, it's kind of okay, and the amplitude too is okay. If you look at the dependency, so in of the with the confining pressure for the X component and the Y component, the dots are the experimental result. It makes sense. So here the idea is that everything is like only the elasticity of the media is changing between each pressure step. Okay, I just changed that. I just changed the wave elasticity, and it's homogeneous propagation for an elastic media, and it looks like it explains the data. If you look at the amplitude dependency, and that's what the model gives us, and we had to add some very strong attenuation to explain this curve. And this is for the pistol and crossbow. The checker is very low, and the rifle it's like saturating our system, and the attenuation is quite strong. So it and this attenuation, I think that's why I ask you. This attenuation is not due to the scattering, because I mean the wave speed, the wavelength is huge compared to the grains. Okay, so now if we compare the impacted wave speed and the shaker ones, you have something that with the noise that we have, the noise is the uncertainty here is 5. We just do 5 times the experiment, and we have well, it's not it's repeatable sometimes, and sometimes we have differences. So somehow it's very close between the checker and the impacted waves. We cannot see a clear dependency between all the different dispositifs we use. So the kinetic energy dependency is not clear. And we have decided that 50 centimeters away from the impact, we don't see the difference clearly between very little vibration from a shaker than an impacted waves. So probably this dependency of the pressure is important in the way the asteroids will react to an impact. And well, just last stuff is if you do the average of the wave speed and you try to explain how it increases, effective medium theory tell you that it should be something like that, p to the 1/6 or p1 on the third, and we have a much stronger dependency. And this curve here is just taking what we use in nonlinear rocks, mesoscopic nonlinearity, the elastic media proportional to beta for beta by the pressure. And in this case, we have something that makes sense. So it seems that this pressure range and this wavelength, the granular media looks more like a rock than an effective grain pile. And we have very similar results in the other natural media for the gravel and the sand with a bit lower beta parameter. So it seems that with the angularity, the nonlinearity decrease in this experiment. And I think I'm done. If you go to Uruguay, just make sure you don't see this guy. It can be dangerous. And yeah, that's it. Thank you.